Welcome, everyone. My name is Komal Thareja, and I'm software lead on the Fabric project. Thank you for joining us today for the 15th installment in our Stitching Together Innovation with Fabric users, led by Kong Wang, Ganesh Sankaran, and Prayag Sridhar. Next slide, please. Before we begin, I would like to share a few housekeeping items. The webinar will include a live question and answer session following the presentation. Please note that the chat feature has been disabled. If at any point you have questions, please type them in the Q&A box at the bottom of your screen, and we'll answer them during the Q&A session. Last, this webinar is being recorded and will be shared with all the registrants. We are joined today by our presenters, Kong Wang. Kong Wang is a senior researcher at UNC Chapel Hill. He received his PhD from University of Massachusetts Amherst. Kong Wang has co-authored more than 40 papers with focus on networking, cloud, and distributed systems, and AI/ML for infrastructure. Ganesh Sankaran has his bachelor's in electronics and communications engineering and then higher degrees in computer science engineering. Ganesh has 2 decades of industry experience working for HCL, Cisco, and then for Dell Networking Division. Ganesh's expertise spans across network management, network security, and network operating systems. Ganesh has been a part of 3 startups that developed a mobile application, SD-WAN, and optimal computing hardware, respectively. Ganesh has co-authored 30 research articles and has been the primary contributor on 25 patents, including pioneering contributions to change detection and drop accounting, programming network switches, computing at high data rates, and designing converged hardware for computing and communications are Ganesh's recent interests. Prayag Sridhar is a graduate student in electrical and computer engineering at Northeastern University, working under Professor Michael Zink on FPGA accelerated image processing. His research focuses on DRegX, a novel 2D regular expression engine for directional pattern matching in images, implemented on Xilinx LVO U280 FPGAs using Vitis HLS. The DRegX kernel performs parallel edge detection, value range analysis, and gradient matching across 8 directions, achieving 7 to 37 times speed up over CPU and sub-milliseconds execution times. His work leverages Fabric Testbed for distributed FPGA deployments and benchmarking across heterogeneous computing platforms, including CPUs, FPGAs, and GPUs. Next slide, please. I'll now pass it on to Kong to start the presentation. Yeah, thank you.
Thank you, Kamal. Hi everyone. I'm Kong, and I'll start the presentation, and then Ganesh will talk about Ganesh and Prayag will continue on the presentation. So here is the brief outline of the talk. So we'll start with some introduction on FPGA for people without like FPGA background. And then we'll talk about how you can find FPGA resources on Fabric. Then we'll talk about the image processing with FPGA and the concepts and the challenges and why we use FPGA for image processing. And after that, we'll talk about our work on the 2D regular expression image processing that uses FPGA. And finally, we'll give a demonstration on how we do the 2D regular expression image processing on Fabric FPGA hardware. So FPGA stands for Field Programmable Gate Array. So FPGA is a reconfigurable hardware. So it's unlike the CPU where we write software instructions. On the FPGA, we are configuring the hardware itself. So one of the biggest advantage for FPGA is that like it provides the hardware level programmability. So we can create a customized processing pipelines without redesigning a new chip from scratch. So FPGA provides a massive parallelism which allows us to conduct multiple operations simultaneously in order to dedicate the hardware on the dedicated hardware rather than sharing the CPU cores. Because the processing pipeline is fixed in hardware, FPGA can provide deterministic delays, which is very important for many applications that require real-time processing or like networking, which require like very little delay, and also the scientific applications which might require the high throughput processing. So another key advantage for FPGA is that it provides the reconfigurable deployment. So the same FPGA can be reconfigured for different workloads, and which will allow the researchers or operators to adapt the hardware as like the requirement evolves. And finally, the modern FPGA platforms provide extremely high performance I/O, including the high-speed Ethernet, PCIe, and like the memory interface and the hardware accelerators, which provide us broad ways for the FPGA usage, including like the signal processing, data center acceleration, or even the AI inference. So why we use FPGA? So FPGA serves as a accelerator platform that can be applied on both networking and the general computing workloads. So by implementing the application-specific logic directly on the hardware, FPGA will enable highly parallel processing that is difficult to achieve the efficiency on the traditional CPUs. And also on the networking side, the FPGAs are widely used for packet processing and for the traffic monitoring and like telemetry or encryption and maybe like the deep packet inspection and many other in-networking applications. So these workloads naturally fit on the streamlined architecture. And also the deterministic delay on FPGA will give us like significant low delay for implementing the in-network processing capabilities. Beyond networking, FPGA can also be used as a general accelerator for compute-intensive applications such as data analytics, scientific computing, or like video processing, or like AI inference. So instead of executing the instructions sequentially like a CPU, FPGAs can create a customized hardware pipelines which can be tailored for specific workloads. So this can provide a significantly higher throughput and low latency. So the key advantage for FPGA is that they are massive parallel and reconfigurable and also provide us deterministic behavior. So because the functionality is implemented directly on hardware, the FPGA can provide predictable performance and with very low latency and high energy efficiency, which we'll see from our demonstration comparing to the general purpose GPUs or CPUs. So people might ask like how FPGAs are so useful. How can we find FPGA resources on Fabric? So whenever you go to the Fabric homepage, the fabric testbed.net, you'll be able to see this map over there. And like once you click on any, you hover over any of the dots, you will be able to see a list of resources on that specific site. For example, if we hover over the Starlight site, we'll be able to see the like list of resources on Starlight, and at the very on the near the bottom, we can see the FPGA. We see there's totally one FPGA on this site, and currently this FPGA is not available because other people are using it or like it's reserved for some other purposes. So if you click that specific site, you will be able to see a list of different sites. then you will be able to find out the FPGA on many more sites. For example, like we can see from this list, there are like many different sites listed, and almost all the FPGAs are available on these the first page sites. So you can go ahead and reserve FPGA on this specific site. And if you click that specific site, you'll be able to see some details about the hardware on that site. For example, like if you click that, I think that's still one of those sites. You'll be able to see the specific FPGA that's available on that site. We have the Xilinx U280 FPGA on that site. Currently, it is available because we can see it's over here. So which is a good news. You can go ahead and reserve and make use of the FPGA on Fabric. Next, Ganesh will talk about the image processing on FPGA, the concepts and challenges. Ganesh, go ahead.
Thanks, Sean. We will quickly look at the image processing a little bit so that we can understand the context of what we have implemented, and we will be able to appreciate better the results that are going to be shown by Prayag later. Can you move on to the next slide? Image processing is a critical part of many of the real world applications, including traffic analysis scenario that we are looking at here, and also many autonomous driving use cases and scientific computing use cases primarily use image processing as its core. Here we are actually talking about object detection, where, for example, we need to recognize a person who is crossing the pedestrian using the pedestrian crossing. In that case, can we actually recognize that person and then see if there are any threats or something like that when they are actually crossing the road? There are actually a couple of problems with respect to the general image processing literature. One of it is the computation of integral image, and the next one is the scale variation, rotation variation. These are some challenges that we will look at pretty closely in the next few slides, but we are just calling them out here. Next slide, please. What is an integral image? Integral image, as it is defined, it is the sum of all pixel intensities in the rectangle from the origin to the current point. That actually gives the total sum. In some way, it's like a 2D integration type of a thing along the x-axis as well as the y-axis. And if we need a particular rectangle, for example, A, B, C, D, and the pixel intensities that are within that, then how do we compute that? Is using the formula that is given below. The sum of the pixel intensities within the rectangle is D minus B minus C plus A. Basically, we are kind of like when we subtract B and C, we are actually kind of like 2 times we are actually canceling the effect of A or the region corresponding to A. So we are actually bringing that back into the equation so that it is going to stay the same. So with this kind of like math that goes behind the scenes for the image processing. This needs to be computed for a large image. For example, if it is a 1024 cross 1024 pixel image, then we will have to compute the integral image for the whole image and then keep it ready so that we can perform some custom rectangle calculations, and then we can actually detect whether an object is within there. Please move on to the next slide. The next thing, after we actually, this is a pretty computationally intensive process that we looked at. After that, there is also a little bit of scaling issue. To consider that, we are taking a couple of triangles within the grid. For example, I'm taking a 10 cross 10 window and I'm trying to see if there is a triangle within that, then the left-hand case actually perfectly fits that, and then it is able to identify the triangle. But whereas in the right-hand side case, we see that the triangle is actually larger than the grid. So we need another grid, possibly like a 15 cross 15 grid, pixel grid, or a 20 cross 20 pixel grid, so that we can actually detect that triangle. So this is the scaling issue that we are actually talking about, and we need to kind of like use multiple scales in order to detect the object successfully. Next slide, please. So the other problem is actually, this is a very rough representation. For example, if we are actually learning everything from an upright position, and there is a little bit of a change in the orientation. For example, the object is rotated by say 30 degrees or so, as shown in the right-hand side figure. Then we need to actually relearn the features again for every pose, every rotation, and things like that. So, for example, this is a two-dimensional object that we have taken, hypothetical two-dimensional object. But in case we are going to consider a three-dimensional object, we pretty much need multiple poses, as we will see a little later. But the key thing here is we need to relearn the features. This is very similar to, like, for example, if you have enabled biometric detection on your smartphones, then the first time it has to learn your biometric signature, you'll have to actually, for example, if the fingerprint sensor needs to actually, you need to rotate your finger at multiple angles so that it kind of learns it properly. So that's the problem that we are actually talking about here. So we need to accommodate different scaling, different size of images, and different rotations. So, and still we need to be able to find the object. Than that. Can we move on to the next slide, please? So we are taking one specific algorithm called hard cascade, which actually uses rectangles, and then it uses a black rectangle or a shaded rectangle and open rectangle, which is actually kind of like one embedded into the other. And then it actually computes whether there is some information within that particular region. So for computing this, as you can see, we have to actually create a rectangular grid and then slide it across the entire image to be able to see whether there is a match. So this is like, for example, if we take a big, large size image, then we are looking at approximately like 60,000 windows or rectangles that we will have to create per frame. And then for the number of scales that we saw last time, like 10 cross 10 is a different scale and 15 cross 15 is a different scale. So the number of scales that we want to actually examine is going to actually multiply the number of rectangles that we have, and then the number of features that we are going to consider, and the rotation, impacted features that we are going to consider, that is also going to impact. So totally, we are actually looking at an order of magnitude of calculation that is actually kind of like grows with the number of scales that we want to consider and the number of features that we want to consider. So this is the key problem, scale type of a problem that we are facing. But fortunately, there are hardware like FPGAs and GPUs that have immense parallelism and make it look like it's an easy task. So they use like thousands of cores behind the scenes, and then they compute things in parallel and make it complete the computation within the order of milliseconds. Can we move on to the next slide? So this is, for example, if we are going to go with the traditional approach, then for every orientation or the pose, we need data sets that are both positive that actually have positive frontal face. And then we also need to have an equal number of negative cases so that we can distinguish the frontal face from, say, for example, a football or some other object that is going to resemble to the frontal face. We need the same thing for the left profile, right profile, and whatever pose that we want to actually detect. So this quickly kind of explodes the number of data sets that we need for learning, and then so that we can detect a face. So we are just taking a single example of a face that is actually detected, but let us consider an example of multi-object detection type of a thing. So every object needs so many number of data sets behind the scenes. Can we move on to the next slide? So while the left-hand side part of it is the traditional way of actually looking at the image processing algorithms, which require in the order of 30,000 and even millions of images is actually used in some cases for accurate detection. So that's the kind of scale that we are looking at on the left-hand side. And what we are proposing here is a regular expression-based image processing, which uses simple semantics of the particular object in order to detect that. For example, let's take eye. Eye has a white outer element, and then there is a colored ring around the center, and then there is a dark central dot. So if we actually use this, so instead of inferring the same data from about thousands of images, we have this clear description that we know from our knowledge, prior knowledge of inspecting the eyes and how we actually the physical appearance of eye as we see it. So we can convert this into a regular expression that roughly looks for something like a light pattern followed by a dark pattern followed by a black pattern, and then a dark and then light. So if we actually look at it, we will be able to quickly isolate the portion of this. But definitely, in order to differentiate this from, for example, football that is having some color drawn pattern which resembles an eye, definitely requires additional effort. And that is where actually we can quickly relate without having to use a data-driven approach that we have been traditionally using. So this is more like a description-driven, and in several other cases, what happens is we use generative AI in order to, when the data samples are very less, in order to actually create more samples, and then we actually infer from there. But a lot of these things can be eliminated if we can actually go with the well-known knowledge base and then convert it into a regular expression and use a small set of samples to validate. Can we move on to the next slide, please? So how regular expression naturally adapts to scale. Here we are actually looking at two different scales where a different number of A's, B's, and C are present, but the same regular expression A plus B plus C plus is able to match both this. So this actually is closely related to the previous example where if you are looking at a 10 cross 10 grid of an eye, you can actually, that resembles the first case, whereas like a 20 cross 20 grid is going to resemble the second case. So it naturally adapts to the scale using certain regular expression operators. So scale is not a problem with the regular expression. So what exactly is the problem? Moving on to the next slide. So where the key problem is with respect to regular expression is it is actually defined on the one-dimensional character set. So it is defined on, in other words, a character sequence. So how do we actually use the same concept on a image that is actually two-dimensional? For example, in the image, you can see so many directions like north, south, east, west, or like in other words, you can also say like up, down, left and right, and then the middle directions. So if we have to actually look at some of these directions, so we define the same regular expression, but then we make it uh, direction agnostic. For example, if there is a rotation, the regular expression remains the same, but we are going to look at it from a different direction. For example, like if it is completely rotated 90 degrees, then we are going to look at it the same regular expression, but in a north-south direction. So that's the key thing that we have actually brought in from a 2D regular expression perspective. So it is direction agnostic. So what else we are actually trying to do here? We will see that in the next slide. So in addition to the direction agnostic property that we have brought in with the 2D regular expressions, we are also looking at the first order and second order and higher order differences. So with first order, higher order differences, the effect is pretty similar to the first order differentiation and second order differentiation, and it helps us to actually classify our sharp edges with the first order differences, and then the peaks and troughs with the second order differences, and so on. So this is additional thing that is going to give us a little bit of like illumination agnostic. For example, like we are having an image that is over illuminated or under illuminated, still the features remain the same. But the illumination actually changes the pixel intensities. For example, if all the pixel intensities are going to go up by, say, 100, then once we subtract that 100, we will actually get the edges. So that's the kind of analogy that we are actually using with the higher order differences. So can we move on to the next slide, please? Now I'm going to hand over to Prayag, who will talk about the FPGA implementation and the evaluation. Thank you.
Good afternoon. Mm, so, what is the deregex for image processing? So the core idea is simple. We take a regular expression, the same pattern matching tool you use on text, uh, and apply them to 2D image data for object detection. A pixel row becomes a string. A pattern becomes detector. Two innovations make this work on real images. First, the tilted object detection. We scan it in 8 directions, not one. So a rotated edge still matches. Second, the lighting invariance. We match it on first order differences between neighboring pixels, not absolute brightness. So feature holds up under a shadow or glare. On the FPGA, we run on all 8 directions in parallel, one results per clock. Uh, Three modes cover the useful cases. Mod 0 finds the edges where the gap between the neighbor and a pixel crosses a threshold. Mod 1 finds the value runs pixels inside a brightness band held for a, minimum length. And it's good for solid dark regions like an iris. Mod 2 finds difference, consecutive increasing or decreasing steps, which captures uh, gradients regardless of lighting. Next slide. Mm, So coming to the FPGA kernel, so that data flow is pretty simple. So the data flows runs HBM2 tile loaded and then it loads to BRAM tile buffer to DDR results. The image sits on HBM. Uh, the loader pulls a 66 by 66 tile into on-chip BRAM. The three compute units like do edge, do range, and do diff work on the tile. Results go on to DDR. The synthesis numbers are on the headline here, so which is 346 megahertz fmax on all loops and zero timing violations. The resource usage is pretty tiny, which is only 3%. So 97% of the chip is free, which is what lets us scale to many instances later. The build flow, coming to the build flow, the whitest HLS is in about 30 seconds. So exports the XO object in about a minute. The V++ link steps in about 2 hours. Deploy in about a minute. So the link step dominates. So the XO and the bit streaming is done in Cloud Lab, and then it's deployed to Fabric Indie. Sorry, not India. Yeah, Fabric testbed with your U280 attached over PCIe pass-through. Next slide. So this is the results part. So FPGA is we are using here is U280, and the GPU is the V100, and CPU is like plain Python. So a small image control test, so we know each mod does what we claim before we scale up. Next slide. So two run side by side. So uh, edge in all 8 directions with diff threshold about 20 finds about 2120 matches in 0.439 milliseconds. Vertical only finds 1181 matches in 0.335 milliseconds. The difference is the point. All 8 direction traces trace to the fully iris boundary ring. Since the ring curves through every orientation, the and vertical only picks up the horizontal eyelid lines because the vertical scan responds to horizontal structure. So the direction set you choose decides which feature light up. This is the rotation invariance claim made visible. Next slide. So there's a okay, and in mod 1, which is of range 0 to 80 with run length of 3 or more, finds around 738 matches in 1.193 milliseconds. It locks onto the dark iris and pupil region, the uh, solid low brightness block. Coming to mod 2, so it increases the difference diffs going down with threshold above 5, finds 191 matches in 0.38 milliseconds. It marks the gradient transition. The places where the brightness ramps because it works on differences, not levels. It holds steady under lighting changes. Range is the slowest mod here because the run length check a change dependent comparison. Next slide. So in GPU V100, we use the same algorithm, but this GPU this was implemented in GPU. So edge all direction, it matches around 1838 in 0.056 milliseconds, and the range is 1058 matches in 0.069 milliseconds. The GPU finds the same spatial features, the iris ring and the dark region. The match count differ from the FPGA, and the honest reason is boundary handling. The FPGA tiles with overlap, so border pixel gets counted. Um, GPU has no tiles overlap, so different edge treatment, slightly different totals. The features themselves agree. Next slide. So this is the comparison table. So we ran the same algorithm in CPU, GPU, FPGA. So as you can see, the FPGA beats CPU by around 37 times across the mode, whereas GPU beats CPU by around 47 to 458 times. On the small image, the GPU wins on runtime, and the reason And the reason is GPU has around 5120 CUDA cores against our 8 parallel directions. But if you see the power and utilization rows before, you can see that FPGA holds a flat 25.4 watt. The GPU draws 60.8 under load. The whereas and coming to resource utilization, FPGA uses 3%, whereas GPU is under 1% of its capacity, but pulls full power. So the GPU buys speed with power, and with cores we do not need the size. The FPGA gives deterministic latency at low constant power, with 97% of the chip still open. And that that open headroom is the setup for part 2. Next slide. So in part 2 we used FFHQ data set, which is which we took it from Kaggle notebook. So it is the real faces of flicker faces HQ, and that data set has around 52,000 images. We run one phase at 4 resolutions: 128, 256, 512, and 1024 to measure the FPGA scaling, and we put it against the GPU on power. Next slide. So 128 by 128 gives around 4,970 matches in 0.681 milliseconds, and 256 by 256 gives 11,891 matches in 1.966 milliseconds. The table tells a scaling story. So if you look at the per tile column, not the total time. So when you look at size 128, it is 0.17 milliseconds. Whereas for 256 it's 0.12 milliseconds. For 512 it's 0.11 milliseconds. For 1024 it is 0.086 milliseconds. Total latency grows with tile count, which is linear and predictable. Per tile overhead drops as the image grows because the fixed setup costs are spread across the more useful work. Bigger image runs more efficiently per unit time. Next slide. If you so the 512 by 512, it matches around 32,076 times in the 6.758 milliseconds, and 1024 by 1024 has around 31,701 matches in 21.967 milliseconds. So notice the match count going down at the higher resolution from 32,000 to around 31,000, even though the image got longer. The reason is upscaling. It's smooth gradient, and some of the softened transition fall below our threshold of 20, so they stop registering as edges. This is the threshold sensitivity to resolution, and it is the real property of regex style matching. The rule is fixed, so a change in the underlying signal shift to what crosses the tile, and it's worth flagging as tuning consideration, not a bug. Next slide. So this is the comparison table of FFHQ scaling. Coming to the energy table, the GPU is much faster, up to 750 times at 1024, and because it finishes so quick, it wins on energy per frame too. And coming to FPGA, it's different. So power is constant at every size. Latency scales linearly and predictably, and jitter stays around 0.05 milliseconds even at 1024, and a line to land on coming to which is the resource utilization, we use around 3% of the chip. Around also we can upgrade it to many instances in the future. And GPU scales from power from 62 watt to 114 watt as the image grows. So the trade-off is raw speed and per frame energy on the GPU against fixed power, deterministic power, and parallel instances headroom on the FPGA. Next slide. So the key takeaway and the future work. So what the paper contributes is a novel 2D regex algorithm for image processing with a working Vitis HLS kernel, and it's deployed to Fabric in Fabric testbed. The HON is 3 platform comparison, so where the GPU wins, and FFHQ scaling with linear latency and flat, which is and constant power, which is flat 25.4 watt. So and move to a larger uh, move to move to a larger 514 by 514 tile, which cuts iteration counts plus multi-instance scaling. Um, so coming to future work. So the future work is like a full regex FSM in hardware with quantifiers and alternations, and video stream processing at real time, and distributed FPGA processing across the fabric network, which is what makes this testbed the right uh, uh, home for the work. Next slide. So coming to the demo part, I'll be sharing my screen. Is my screen visible? Hello.
Yes. Can you remove the Zoom window?
Oh, okay.
Visible.
So this is the demo. So the step one is to write the token. So the token can be obtained in yeah in this link. So which is the cem.fabrictestbed.net. So and yeah, like you're supposed to create a token. It's very important for the experiments to run. So this is already expired. So I've already used it, and it's not recommended to share your a token to anybody. But since this is expired, so I'm sharing it. So you have to copy paste this to this place of token JSON. So between these to a token JSON, you have to like paste it here, and then when you run it, it shows like token state as valid, and then we have to run the Fabric manager to set up the environment, and you need to reconnect the slide. So there are times when the slice gets expired, and you get to see such thing like a slice not available. So for that you have to run this command, which is try, and when you run this, it will show like low LOSA active. So when it shows active, then it confirms that slice is created. And the next step is to install the XRT on fresher node. And after that, I have to verify whether you have to verify the XRT and the FPGA card to confirm whether the installation is complete and valid. And verifying the bitstream host and images. So so you have to confirm whether the files were up like you the files is uploaded to the slice. So but initially you upload the required files using this tool, upload files, then you need to push it to the slice from the Jupyter hub to this particular slice. So it shows. So when the file is available, it will show like this, like face, you know, and yeah. So and then the next step is to recompile the host. This is to check whether the file which we are supposed to be experimenting on is compiled properly or not. And after all that, after I are supposed to check the the next is the runtime. So before the runtime, so you need to check whether the required files is pushed, because sometimes like the required files when you try to push the required files to the from the Jupyter hub to the slice, it shows error. So by this line, it's confirmed that it's pushed. And so timing. So the first we are going to evaluate the timings. So for the ICE, which is 77 by 77 configuration, sorry, not configuration, resolution. So you can see that at one computing units, the runtime is around 0.112 milliseconds. And at 8 computing units, it's around 0.268 milliseconds. So so now a question might arise, like why is 8 computing units, which is 8 instance of parallelism, slower than the 1 instance? That's because I is a so this particular image which we are evaluating, it's pretty small. And so and since the what we built, it is for the bigger images. So for smaller image, it would take a little extra time for the evaluation. So for mode 0, it is so these two are the runtime. So for mode 1, it's 0.402 milliseconds, and for when it comes to 8 computing units, it's 0.427 milliseconds. And the same for mode 2, it is 0.263 milliseconds for in so 1 computing units, and in 8 computing units, 0.355 milliseconds. And this is the runtime of the FFHQ images. So as you can see, so 128 by 128. So for 1 computing unit, it is 0.445 milliseconds, and for 8 computing units, it's 0.523. So as you if you observe, it's the like 1 computing units and 8 computing units. Sorry, 1 computing units is little faster than the 8 computing units. So yeah, like the reason is, as I stated before, so the image is small and the over head effect takes place. So and when you look at 256 by 256 resolution, then you can see the exact opposite. So the 8 computing unit the results is 0.819 milliseconds, whereas for 1 computing unit, it is 1.778 milliseconds. So so you can see the parallelism and pipeline process taking place. So and it can be observed that 8 computing unit. So as the resolution increases, the parallelism effect takes place. So that's why 8 computing units and is much more faster than 1 computing unit when it comes to 256 by 256. And if you see the 512 by 512, it's the same. So at 1 computing unit, it's 7.122 milliseconds. At 8 computing units, it's 2.001 millisecond. And in 1024 to 1024, you can see that at 1 computing unit, it's 29.846, but at 8 computing units, it's around 8.224 milliseconds. So it's 3x times. So the 8 computing units is 3x times faster when compared to 1 computing units, when you observe when you take 1024 resolution into consideration. So Step 9 is the visualization process. So this is the code for the visualization. So this is the original image, and this is the edge detection image. So and it was completed in 0.324 milliseconds, and this is so for a range which is mod 1. So the first image is mod 0, second is mod 1, third is mod 2, which is the invariance differentiation. So these are so the edge detection can be classified to 8 different directions. So first is edge right, uh, and then edge left, and edge up, edge down, edge down right, edge down left, edge up right, edge up left. So uh, next part is about the FFHQ images. At 128 by 128, so this is the original image, and this is the edge detector image. So edge all, and this is the same 128 by 128, but this is a range which is mod 1, and this is more mod 2 at 128 by 128 resolutions. This is 256 by 256 resolution. So if you observe like 128 and 256, so you can see that 128 is slightly blurred compared to the 256, which is enhanced. Now, so when 256 by 256 is run, then this is the image we get. So so this is edge detection, then range and invariance differentiation. At 5 and 2, at 5 and 2, this is the original image, and this is the edge detected image. And for 1024 also it was run, and this is the results we got. Yeah, so that's it. That is the demo part. Any questions?
We'll now transition to the Q&A portion. So Kamal will be our facilitator. If Kamal and all of our panelists want to come off camera.
First question is like, is the regex for an eye handwritten, or is it automatically trained from many photos of the human or animal's eyes? And how could the system distinguish between an eye of a human or an animal and a bull's eye shooting the range target or a paper?
That's a very interesting question. Let me take that. Currently we are actually using the eye descriptions and then converting that into regular expressions. We are not using the data-driven kind of an approach currently. And then the next part of the question is about differentiating an eye versus a bullseye. Like we discussed during the webinar, we are still actually in the phase of detecting an object and not really into the differentiation part. Thank you.
Detecting just an eye required 3% LUTs. If I want to detect hundreds of different object classes, that is hundreds of regex sets, for example, eye, ear, tail, how much resources would be needed? In other words, what portion of the 3% LUTs are fixed cost and what percent would grow linearly proportional to the number of object classes needing detection?
Mm, it's like it's also dependent on the parallelism. So, like I showed you the parallelism instances as well. So, um, and parallelism is required. We are to run the experiment in the shorter time. And coming to the next part, like we still haven't explored more. Like we are yet to do more compare. Like as of now, we did only the FFHQ and the I. That's it.
And is the demo code available?
Yeah, it's available. Like, should I post it in the chat box or?
Maybe you can share it with Chelsea and we can share it with everyone with all
Yeah.
the resources. Okay, thank you. Why is it necessary to manually obtain a Fabric token and paste it into your Jupyter notebook? Normally, the hosted Jupyter lab can obtain a token automatically. Is there something special in GPU FPGA experiment that requires this unusual procedure?
Not really, actually. We can use, if we are using the hosted Jupyter Lab, like the question says, the token is obtained automatically, but we kind of like some of the custom environments, like for example, I use Visual Studio and Visual Studio Code, and there we need to actually plug in the tokens. So it depends on the environment, actually.
Okay. And the last question is, what Fabric resources or FPGA node types were used, and what hardware specifications should someone look for if they want to recreate the setup?
The FPGA node which it was used was LOSA, which was available in Fabric. Coming to what hardware specification should someone look, so it is U280, which and 2022 version. So that is what was available in the Fabric.
Okay. Thank you. I'll pass it on to Chelsea.
Thank you.
Sure. So thank you everyone for joining today. In addition to the presenters that presented today, we would just like to thank the folks behind the scenes that put this webinar together, myself and Casey Wang. For our next webinar, which is going to be on mastering Fabric tips and tricks and it's going to be on July 21st at 3 p.m. This webinar will be focusing on existing users, AI researchers, and testbed administrators. And so we would appreciate it if you could forward this information to any relevant users in your communities. And then just as a final reminder, as we close out, please make sure that you are submitting your Fabric matrices. We use these when we are doing outreach, and we would like to include them on our website. And with that, thank you all so much for joining today, and I hope everyone has a good one. See you next time.